Thank you, Paula. So, as I said, I've been working in flow cytometry core facilities for quite a while now, so I've seen a lot of instrumentation. We are located in Amsterdam in this nice new building on the 11th floor. We're actually a merger between two teaching hospitals, so there's one further to the south, but we're both on the south end of the city. We have users from this site and then also our main site, but most of our, about 70% of our users actually come from within the molecular cell biology and immunology department. And here's our, here are our flow labs. And then we also have some analysis rooms that people are able to use. Okay, there we go. Okay. I'll try using the screen instead. Oh, this screen here. That works? No? Okay. Okay. So this is our suite of instrumentation that we have in the cytometry part of the microscopy and cytometry core facility. We have a few sorters, we have some spectral analyzers, a emulsion single cell droplet capture system, a mass and imaging cytometer, a few kind of more standard analyzers, and then what I'll be talking today specifically about is the Attune CytPix, and we'll head more into that. And then of course always what's kind of the core of the core facility is the actual people. So we have 2 FTEs, including myself and one other operator in the facility, and then 2 part-time FTEs that are more like 100% time. So I just want to do a little advertising about my core facility myself before I jump into the instrumentation, because that's where I'm at and that's what I do. But yeah, now a bit more about the CytPix itself. We've got the Thermo Fisher disclaimer down here, just so you guys know. This is, of course, for research. This is not for clinical diagnostics, just to get that out of the way. And here inside, you can see some of the internal components of the CytPix itself. So here you can see a 20x objective pointed at the flow cell itself. So in this instrument, our flow of sheath is actually heading up rather than down, as you might think of on a sorter. Many instruments are designed this way, but within this flow cell, we also have this objective pointed here. There's a periscope, which then takes the light that's captured and points it at this camera that's up here. And so what we're able to do is get your standard fluorescence data and light scatter data. So same forward and side scatter that you're used to seeing, plus your fluorescence channels, so those FCS, that FCS information. But then it's additionally coupled to images which are taken of these events. Now these are Brightfield images, these are not fluorescent images, but just the same as how forward and side scatter are very powerful about telling us some information about the morphology of the cells, now we're going even deeper with these direct measurements. We can actually observe these cells now. We're not just relying on light scatter. We can see what the cell is that corresponds to that fluorescent information. And the reason why it's got the Attune tagged in the front of it is because it is an acoustic focusing flow cytometer. So this technology has been out for several years now. And what this allows for is increased speed of your sample. So being able to just run larger volumes at a higher speed without that increased variability in your data that happens with the expansion of the core of a stream. So as you can see with a conventional flow cytometer right here, you increase the pressure of a core of a stream and you can have translocation, which means your lasers are actually hitting your cells or your objects of interest at different locations, and so you end up with different number of photons, so less power hitting your cells depending on where they're located. But the acoustic focusing function allows, on top of the hydrodynamic focusing, to have those cells just go one by past the laser while having that increased volume running through the system. So a lot of you maybe already know about the acoustic focusing function, but this is our CytPix as it stands in our lab right now. I attached little googly eyes because it can actually see your cells, so I thought it was appropriate. Makes the instrument a little more fun. And our imaging specifications, just to dive a little bit more deep into just kind of this, I should say deep into the surface levels of technical details on the CytPix itself. So the field of view on the camera is variable. You can choose different regions on the camera. And you can select those regions to be from anywhere from 96 by 96 pixels all the way up to 248 by 248. Each pixel is 300 nanometers, so that gives you this total field of view. You can go up to encapsulating cells. You can image cells that are up to 74 microns in diameter. And then the illumination is variable, and the focus is variable, so you can illuminate and view your cells in different ways. It's all just right now based on what you think, how you like the cells to actually appear. So you can have a darker illumination, you can have, since this is all projection imaging, where you're just seeing the entire stack of you're seeing the entire cell, and so you can focus either on the center of the cell, you can focus on the edge of the cell. The way we tend to run the system is just to be focused right on the center of the cell. The peak resolution is around 600 nanometers. I've been able to image beads that are even smaller than this, but they mostly appear as kind of like a shadow sometimes. I've even been able to image individual synapses, neuronal synapses from mouse brain before. And then our kind of reasonable real-world acquisition. So the 6,000 images per second is what you might read in the Thermo Fisher catalog, but I found the reliability, you can image about 2,000 events per second very nicely. So to go a little bit more deeply into the acoustic focusing function, and now we can actually see that in action. So just backing out to kind of a very fundamental part of this technology, the acoustic focusing. So here you can see these are 14 micron beads imaged. And so this is being run at 100 microliters per minute with, 15 micron polystyrene beads with the acoustic focusing on. And then the second that I turn off the acoustic focusing, you can instantly see how these beads are actually not being centered exactly in the middle. And so this is a really nice teaching tool for people. So rather than just looking at histograms and seeing the CVs increase, you can literally see inside the flow cell how those beads are translocating within that flow cell, so you can see how they wouldn't be actually hitting the lasers at the same point every single time. That, of course, is increased even more when we're running at 1 milliliter per minute with the acoustic focusing off. Just these CVs are all over the place, and just to prove it, can pull up a histogram of just the forward scatter here. And you can see this is the 100 microliters per minute is kind of your top speed for around the top speed for any most other common analyzers. But then you can go much faster without increased CVs, but the second you turn off that acoustic focusing, you can just, you can see kind of the principles of the acoustic focusing plus the laminar flow. So here you can see with the 100 microliters per minute. Where's my mouse? There it is. With the 100 microliters per minute, that the laminar flow is actually keeping those beads pretty centered, but eventually that is lost. So as a core facility person, I'm always thinking about like new people coming to the lab, coming to a flow cytometer for the first time. So if you're really experienced in flow, all of this is just like, no duh, of course we know this. But when you're new, just learning, being able to see that this is really what's happening and this is why, and it's not just our educational materials, but people can easily, quickly pick up this instrument and start running their samples themselves and see this, it's invaluable for teaching new users. So then actually getting into the cells, which is probably what most of you like to hear a bit more about. So this is kind of one of the first projects that we tried out at the instrument. So a user came to me, a researcher, and was trying out a very, very simple detection for circulating tumor cells post-surgery. And so they had this first experiment where they were spiking in 10 cultured tumor cells into PBMC isolation, 100 just different spike in concentrations of these cultured tumor cells. And we could find them, and we could find the concentrations that were actually spiked in. It was really nice. And so we wanted to kind of go beyond that and see, like, one of the big problems for them was the fact that they were having a hard time seeing really any differences from kind of healthy donor versus post-surgery donors. They were seeing kind of like these tumor markers at a slight increase in surgical patients. But it wasn't enough that they could really say, like, okay, yes, these are tumor cells. And so it didn't really work out super well in the end, which actually is really nice, because these researchers were able to essentially move on from this project. So it's also important for us to always communicate failures, which is kind of what stands out to me in the core facility, is when things don't work out. And I think it's important for us to communicate that, so that we're not all kind of like trying to do the same thing over and over again and failing. I think we've all kind of heard that proselytized in research. But for this example, we're looking just to, when we finally wanted to validate this assay, we're looking at healthy donor PBMCs. 500 images were taken for these cells. So this is a top-level gating. This is just our imaging gate. No kind of doublet discrimination, anything like that has been done yet. But then when you do go into that doublet discrimination, you can see that we indeed have single cells that are positive for these two markers here. And so, yeah, that's interesting. You're able to see that indeed there are single cells there that are showing up positive for these two markers, so kind of like false reporting essentially there. But also it didn't really like correspond to kind of the morphologies and maybe something that we could predict in these samples. And so when you actually look at the patient donor samples, here again we're at the top level, it looks about the same as the healthy donor. And then as we dive in, you can see once we actually start looking at these images, there's nothing that we can kind of faithfully be able to train a system on to be able to identify these as being distinct from our healthy donors. So this project was kind of left behind. Everybody was able to save some time and effort. Of course, there are other ways of validating these systems, but what they were looking for was something that was really, really simple and straightforward. They didn't want to do sorting and sequencing and all these other things, and so this was able to get us kind of to an answer that this maybe wouldn't be a great project to continue forward on. And so we also had a researcher coming from another department who has been working with a company for a while. They've been producing just a lyophilized antibody panel, so everything already in the tube. And every once in a while, these researchers were getting really, really high PE signal, which is indicated in this image gate. And they were curious if these were actual cells or antibody aggregates. Again, wanting to do this without doing kind of additional steps. So having to sort out these cells, having to do kind of more time-consuming and labor-intensive ways of actually validating what falls within that gate. And so we were able to just take images of the really high PE signal. Nice, easy, simple, straightforward experiment. And when we actually look at that image gate, there was pretty much all of the objects in here were actually appeared to be due to sample preparation, so cell aggregates, nothing that really appeared to be antibody aggregates themselves that seem very, very obvious. I mean, albeit, of course, there could be antibody aggregates that are bound to the cells, but just the idea that there were loose antibody aggregates themselves that were showing up as objects that were actually getting through our initial doublet gating was kind of disproven. And then, yeah, you can see here kind of our initial forward and side scatter, and then standard doublet gating on the forward scatter area and forward scatter height. You can see again that indeed those are not just, those don't appear to be antibody aggregates to me. And so something that maybe people are a little bit more familiar with, if kind of want to dive in more here into the coincidence gating and just trying to get us to think about more about just what is standardly done with all flow data. If anybody here is analyzing flow data, generally you're doing some kind of data cleanup that usually involves a forward and side scatter gating, that usually involves doublet gating, live dead gating. So just all these things to clean up your data so that you know that you're only analyzing a single cell in most cases. Flow has all kinds of applications, but let's just reduce it down to analyzing just a single cell. And so you want your gating to be, you want it to be robust. You want to know that it is working every single time. However, the CytPix is revealing to us that that is not true. Maybe many of you have projects out there where this doesn't really matter. You can have a little bit of noise in your data, but there are going to be people in this audience who want to look at rare cell types, who want to look at large cell types. And so I wanted to just show an example of hex cells because they're rather uniform in size and morphology. And so differences in scatter are differences in the scatter parameters, so the pulse parameters, your area, height, and width, how we actually pull out these coincidence events and exclude them from downstream analysis. You would think that this would be very consistent and very reliable. And so if, again, just very, very basic gating here, forward side scatter, doublet gating, you can see that indeed there is out of, what is this, 36 events, there's one doublet. So does it really matter? What I would say, just to show a little bit about this software, what's really nice about it is that I can actually select this doublet event and backgate it so I can show where this event actually fell within my doublet gating and my initial morphology gating. It's just a nice little feature of the software, but of course you probably noticed that you had to decrease the resolution a lot to the lowest resolution so you can actually see where that dot falls, so where that event falls on your plots right here. And so when we actually start looking at what is actually excluded, so what is not being included in your downstream analysis? Very large cells, that is what is not being included in your downstream analysis. This is consistent across many cell types, many assay types. This is happening all the time. These cells are being excluded. And as you can see here, again, if we choose to view these images, you can see that we're viewing the images that have this little eyeball icon here. Again, we can see exactly where those lie on the plot. And you can see that these aren't even really close to our doublet gate. They're complete outliers. And so maybe just a little bit more of a common example, probably cells that you guys analyze all the time, PBMCs. So again, we're going to this area versus height, really nice. Single cells across the board, maybe every once in a while there's a doublet in there. Looks really good. But again, when we go down into what we assume are doublets, what are we gating out here? I would guess macrophages. I don't have a marker for this particular imaging experiment to actually show what these cells were, but they are being excluded. And if larger cells are what you're interested in analyzing, I think you're losing a lot of them in your gating. And what this software can eventually do is help you just analyze single cells with maybe not only relying on your forward and side scatter doublet, pulse parameter doublet discrimination values. And so some people say like more is better. So if you really want to only analyze single cells, maybe you're actually going to start looking at those pulse parameters from your side scatter as well, because we've got area, height, and width. So often the idea is if you have a large increase in width, then you likely have a doublet there as well. But you'll notice I'm viewing R3, which is the same as this gate up here, which is an increase in width outside of the average scatter scatter values of side scatter height versus width. And all of a sudden you can see that indeed there are just a few that kind of have doublets, but in general, the most of them are singlets. So what I'm saying is that these scatter parameters only go so far. When we can actually see the images, we can see what falls within those parameters. Again, here, this has guided me a lot because in general, we want to exclude anything that's kind of an outlier with these scatter parameters. And so you would want to exclude anything that has a really, really high height for scatter. But you can see here that maybe that is actually not a very good idea because indeed most of the cells that are out on this extreme height parameter actually are singlets. So these are really basic things. We all use forward and side scatter, but we're not actually getting all that information there. So then I like to go out to a more extreme example. With this example, we're seeing R2, which are supposed to be singlets. Sometimes it's single cells. A lot of this just has to do with sample preparation. And then if we look at this area under kind of the bulk of our cells right here, again, very large cells that are being excluded from your downstream analysis. So then I like to go to something that maybe you would all commonly see if you're looking at dissociated tissue or differentiated cells, or just cells that tend to be on the much, much larger size range. Looking at your forward and side scatter in linear range with few cells, very, very difficult to discriminate between what is debris and what is cells. Maybe some of you have run into this. It can be very frustrating. And so right here is kind of this R1 gate is our threshold between our cells and debris. We can move down further and you can see indeed then we only have debris in that gate. We move up further and we're more reliably seeing cells. So we found that region right between our cells and our debris. Move up even further, you have really large cells. And then what's interesting are cells that have completely saturated both of those channels would no longer be included in your gating, correct? But for your analysis. But if you actually take a look with these really, really large fibroblasts, so this person is trying to kind of replicate lymph node tissue, so it's really important for them to know just what cells they have in their culture. And so they were, for the longest time, not actually including these larger cells in their downstream analysis. And I know some of you have probably worked, again, with dissociated tissue and large cells, and maybe you have read papers or finally figured out the trick that, of course, you can just go into log scale, and that makes life much easier. You can easily see the difference between your cells and your debris. So we're still looking at CytPix data here. This is where I actually needed to take a user because they didn't know what to do because they weren't sure if, because we can easily enough kind of identify where instrument noise is. So we've got instrument noise down here versus debris versus what we assume are cells. We can also, of course, like use our markers to backgate and find out where cells actually lie, what are positive cells, what are negative cells. But this user had a case where they weren't really sure what was happening in this region. They weren't sure if these were actual cells that needed to be included in their downstream analysis at another instrument. And so I just brought those cells to the CytPix and we can kind of replicate those same scatter clouds. So just finding the instrument noise, you can see its noise here by our images. And then coming up a little bit further, you can see there's maybe like some EVs, something like that. There's just some debris, other things that are left behind this by the cells. And then when we finally come up to here, you can see that there are what appear to be actual whole cell events. And then, of course, we can, just as a comparison, this is how we actually ended up setting up the other instrument based on this information here. So we were able to acquire more just whole cell events without thresholding out too many events, and also including the much larger cells without having too much bias with setting up these detectors to exclude events on the axes. You can still see that there are some here. It's always a struggle in a core facility to really push people in a good direction, but I think this user eventually found a good balance because they actually set up these voltages, and whereas before they were kind of having this cloud really be shoved up into the corner, so they couldn't really gate on it easily. And then just to show where these cells come from in the end. And then this one's just kind of a nicely visually appealing experiment that you're able to do. So we fed microparticles, so polystyrene beads, to macrophages. And macrophages doing what they do, phagocytosed. And here you can see we're looking at what was a kind of 1x bead concentration. The macrophages took up 1 bead. And you can actually select that single bead cloud based on fluorescence. And just going up to the next cloud above, you can actually count 2 beads in there. No big surprises here. I just think it's a nice, real, clear visual representation of how you can actually couple that fluorescence information into a Brightfield image. So then we go up to what we would suppose to be the 3-bead cloud. You come in here and look at the images. You can definitely see 3 beads, 1, 2, 3, 1, 2, 3. 4 beads, etc., until we're up to what's 100x bead concentration, and it's just a macrophage that's nothing but beads. It's just a sack of beads at this point. Which also leads to another ability for me to help kind of teach more fundamental flow principles. So looking at forward scatter, forward and side scatter, increases in forward and side scatter do not equate to size. This is something that people say all the time. Forward and side scatter are refraction, reflection, deflection, and diffraction. And so you can see here that these macrophages have not changed in size. It's just a matter of how many beads are inside. So everyone knows that kind of one of the general flow principles is that, of course, side scatter is internal complexity. So this is corresponding really nicely. So 1 bead, you have a lower side scatter. Many, many beads, you have a much higher side scatter. And then also looking at forward scatter, you can see that the average intensity on this forward scatter plot for cells that have taken up many beads has actually decreased a lot, whereas the cells on average are about the same size. And then I can be even more exaggerated with this example by showing cells here with this little area measurement tool on the software. This hasn't changed between these two. The camera area is the same. All the voltage settings are the same between these two samples. You can see instantly that our cells are nice and on scale, but the second that we go to something that's a lot more dense, you have this huge shift in downward shift in forward scatter and big shift, upward shift in side scatter. Of course, a lot of you know that this is how you're able to maybe help discriminate between live and dead cells. This is one of the reasons. Cells become more punctate, so they're going to decrease in forward scatter and increase in side scatter, but you always want to use that live-dead marker as well. And so here's an example where we were able to kind of confirm what was happening at a sort without me having to go over and mess around with one of the microscopes and annoying our microscopy guys by you just don't want to put me at a microscope. You want to keep me at flow cytometers, not going to a microscope. So this is an easy way for me to know from dissociated tumor just kind of if our gating scheme was working out really well. This is for downstream applications on these microfluidic single cell capture systems. And so we were essentially just picking out CD45 positive versus CD45 negative cells. Really simple sort, but of course we have tumor cells along with our lymphocytes in there. And so actually like picking out those and making sure that those scatter gates actually work out well. It was just nice to have this easy, quick visual confirmation because you don't have that when you go to a microscope. You don't have the forward and side scatter information anymore. So you're able to couple that together and actually see where those clouds lie. You're no longer having to like say, well, I've sorted that and the majority is there, but kind of what actually our constituent parts are within that. And so you can see like our CD45 positive sort is actually really, really clean, but we needed to, we got some nice feedback here that we're getting a lot more debris in kind of our CD45 negative sort, and so we're able to adjust our gates a little bit and improve the recovery of the non-CD45 cells, which is important because, you know, these single cell experiments, they take a lot of effort and a lot of work, and you want to make sure that you're actually inputting like whole live cells into these experiments, because that also saves the bioinformaticians a lot of headaches as well. And then just kind of the final step, kind of the future that we're going with this. This is a lot of just examples of right at the instrument, drawing gates, getting to see the images, it being nice feedback about how you might set your forward and side scatter, your doublet gates, all of this stuff. But of course, people always want to analyze the images, right? And so we've started some inroads, started with actually analyzing these images. So creating masks to identify cells and then pulling out some of these imaging parameters. So, you know, does an image actually just contain a single cell? How round is it? How bright is it? Just some of these basic imaging parameters. And so we can take, in this example, we have images which are clustered upon just the images, and then we have, from the exact same experiment, cells that are clustered on fluorescence, and then we actually couple that together. You can start seeing maybe populations that are looking a little bit more distinct, and of course we would eventually like to be able to take these clusters and see what images fall within that. It's just kind of a work in progress, but this is kind of the future of actually using the images to analyze. But for right now, what I see is just the absolute utility in these Brightfield images to really guide you and get more out of your research. Make sure that you're not losing cells that you want to analyze. Make sure that you're not analyzing cells that aren't actually single cells. This is really important fundamental things for your research and just for the utility of flow cytometry. Flow cytometry has always been a relative measurement. Now we're getting into the world of direct measurements with flow cytometry. And so, yeah, I hope you all have enjoyed seeing kind of the everyday average in the lab utility of such just like a nice, simple, basic add-on that I wish I had on every instrument. For right now, I have to take all of those samples from other instruments to the CytPix, but maybe one day there'll be a nice future where every instrument has their standard forward and side scatter and a nice Brightfield imager. And so I just want to say thanks to people who helped me out a lot at my workplace, the team from Thermo Fisher. Some of these people helped me like build a workshop with different undergrad students at the university. Caroline was the one who did this big circulating tumor cell mock and trial. So she put in a lot of work and also testing out the autosampler at the CytPix, nice autosampler. Marcia is the person who did the macrophage phagocytosis assay of beads. And then, yeah, and it's just been really nice to work with the technical development team at Thermo Fisher, just really being able to try out the software and try out the instrument and really poke it and prod it and see how far we can push it. Yeah, thank you for your time.